Hello everyone. Today I want to talk about orbital hybridization. Using a molecular kit, you can visit a very simple example of carbon bonded to 4 hydrogen methane molecule. And if you were to draw this in 2D perspective, think about these two bonds that I'm ponding along to be on the plane of the paper. And this bond clearly is going away from my body, and this bond going towards my body. So we're going to use the dash and the wedge in order to represent those. So you have carbon in the middle, your central atom. You have 2 hydrogen atoms on the plane of the paper. This represents the bond going away from me, and to represent the one that going towards me, we will darken that, and that would be a solid wedge. And that would be hydrogen 2. Okay, so as we can see clearly, there are 4 bond around the carbon. And if we were to draw the energy diagram for the orbitals, we start with the configuration for carbon. I'm just going to write on the side here, 1s2, 2s2, 2p2. Everything is 2, so very easy to remember. And the 1s is the one that has the lowest energy. It's going to be at the bottom. You're going up the energy level, going up for the electrons or orbital. According to Hund's rule, we half fill them first before we double them up, but carbon don't have enough electron for us to double up, so that's what it looked like. And these are the one, okay, that we call, since grade 11, the valence electrons or orbitals. And these are the ones that involve in bonding. Okay. So now we've learned from the valence bond theory that in order to form a bond, the condition is that you have to have a half-fill orbital. So this is ideal. This is ideal to overlap with another electron from another atom, such as hydrogen, fluorine, for example. So having something double up like this is not ideal to form a bond because they're already paired. So how do we explain for the fact that, well, I need 4 unique bonds around the carbon, but I only have 2 half-fill orbitals to form the overlap? And I also need to remind myself that apparently all the bonds that we do experiment on, they all have the same length. They're all identical. They all have the same energy. And the bond angle are all 109.5. So remember, these are electron clouds. They will situate themselves to minimize repulsions, right? So all of this bring us to the idea that there gotta be some other way in order to make sense of the fact that we need 4 bonds. In reality, we've seen 4 bonds, but on paper, there's only 2 half-fill orbitals that's available for bonding. So what are we going to do? So luckily, Linus Pauling helped us with this, very difficult questions. And using his imaginations, you see in chemistry, you need to be creative as well. So I'm going to redraw that, energy diagram. Look like my pen bleed through here, so sorry about that. Here you go. I'm going to redraw this. So the next step is to make sense of this is that you need to promote this electron into the higher energy level, because once you do that, I'm just going to showing the step where this electron here, I'm going to promote that to the empty shell, okay, or empty orbital in the 2p. Once you do that, now you end up with something like this. So now immediately you have generated 4 different single-filled orbitals that are available for bonding immediately. So the next step you're doing is like blending them up, or we call them hybridizing. So you take that 1s, the s orbital. I say 1 because there's only 1 in quantity, but then there's 1, 2, 3 p orbital looking like a dumbbell or figure 8 shape. You put in a molecular blender, if you will, and then blend them up. And now you end up with, on the other side, 4 chicken drumstick. That's what I call them. That we end up with a 4 hybrid orbital. that we cannot differentiate them. Just imagine this: when you blend orange juice and let's say avocado, whatever come out is going to be a hybrid, and you can't differentiate, oh, which one is the orange juice, which one is the avocado. All you know is that they all mesh together, right? So the number of hybrid orbitals you're making, you end up with the n equal to the number of orbitals that you used in the beginning. So if I use one s orbital and I use 3 p orbital together combined, I have 4. So in a way, the number of orbitals that you get in the end is conserved, right? Okay, and all of them are now identical in terms of appearance and energy level as well. And if you were to put these 4 chicken drumstick around the carbon atom, it's going to end up with the similar shapes like your methane molecule. So we call the shape tetrahedral because there's 4 of them, and they situated in that arrangement to minimize repulsion. So then you end up with 4 identical hybrid orbitals. And now you're ready to bring those hydrogen in to overlap with that singly bond electron that you have there in the hybrid. Hydrogen, of course, bring it on. So you have some sort of pairing and overlapping going on at in this picture here. And that's how we explain bonding. Okay, so I hope it's clear for the methane scenario. This is a very beautiful conceptual idea that chemistry student would need to know. Okay, now let's understand a little bit more about the hybrid business. So some important aspect you need to know is that all the orbital that are hybrid that you just made will be identical in terms of energy and appearance. So in a way, we call them degenerate, okay? So this word used a lot in university, degenerate. And they are mathematical average of all the atomic orbital average, okay? So let's say an sp3 orbital that you just made in the previous page. I forgot to mention that it's actually 4 different sp3. That's the designation of what the orbital is called. All 4 of them is 25% S character and 75% P character, because that makes sense. We use 3 different P orbital in there. And I mentioned this already, the number of hybrid orbital equal to the number of orbital originally combined. And hybridization, please keep this in mind, only take place within the same principal quantum number. So previously you have seen that, it's happened between the 2s and the 2p. It will never happen between the 3s and, the 2s and the 3d, okay, for example. That's what it meant. Now, this step is how to do hybridization for any atom in detail. So the first thing you need to do is, of course, drawing a Lewis structure. Before you can do that, you need to know the total valence electron and then distribute it according to the step I taught you in class. And remember that some molecule might not obey octet rule depending on what the central atom is, especially phosphorus, sulfur, sometimes chlorine, and the halogens, right? And then you do a bond analysis, like count how many sigma and pi bond there are. Remember that pi bonds are the bond involved in multiple bond that you've seen earlier in previous lesson. And number 3 is to draw the valence orbital diagram of the central atom, sort of like what I did earlier for the carbon, right? And focus mainly on the valence orbital, because those are the ones that involve in bonding. And then you need to promote electron if applicable, right? Sometimes you don't have to, and just blend them immediately by hybridizing the occupied orbitals. Remember that if you have a multiple bond, like a double bond or triple bond, remember to preserve the p orbital for those, because they will not be hybridized at all. They need to be preserved in order to form form those multiple bonds, okay? And then, of course, the end is to show the picture of overlapping orbitals in order to form bonds. And I'm going to do example again with the methane molecule. So step number 1, you're going to find the valence electron, okay? So with carbon being 4, and you have 4 hydrogen, each of them have 1, and that is an add, that is not a multiplication sign, and that should be 8 electron, okay? So now we're going to draw the Lewis structure for hydrogen and carbon for the methane molecule, okay? So now we notice that these are all sigma bond, right? And we need 4 different, so this is my bond analysis step. So bond analysis. We need 4 sigma bond. Okay, now the next step that we're going to do is we're going to draw for the carbon the orbital diagram like I did before. And then step number 4, you're going to promote, right? So promote this one up here. And then step number 5, you get. So a lot of redrawing. Okay, now the next step is you're going to hybridize these all. So hybridize all. Okay, I'm going to split this page. Okay, and then it's going to go up here. And I'm going to say that, oh, I'm going to get the result of hybridization. It's going to be 4 identical hybrids that we call them sp3. Okay, 1, 2, 3, 4. So once you take them all and you hybridize them, these things now are gone. They no longer exist. But what exists is the new 4 hybrid that you form. And then the next step would be to show the overlap, right? So just draw the carbon for me and draw the 4 loop. Remember the chicken drumstick. Okay, and then you bring in the the hydrogen to show the overlap between the 2 orbitals. Remember the hydrogen, the only one electron will show you as the 1s, a spherical shape, and is this area of overlapping that form the sigma bond for us, okay? So we've succeeded, and each of the drumsticks is actually sp3 orbital. And if anyone ever asks you about the shape, of course we've done VSEPR by now, and you can add on the perspective drawing. You can say that the bond angle all around is 109.5, okay? No deviation from this. All right, of course the bond angle will change depending on whether you have lone pair or not, right? Okay, so that is for CH4. Now, what about multiple bond? I'm going to do an example for C2H4 right here, which is alkene, okay, double bond hybridization. So once again, you're going to find out the number of valence electron for me, please. So 2 carbon atom, each of them have 4. And then we have 4 from the hydrogen, a total of 12 electrons. And then we draw the Lewis structure. That's going to look like this. Okay, that look like I have distributed 12 electrons, and my carbon have 8 electrons around each. They should be happy with an octet. And this is my pi bond, and this is my sigma. right? Double bond are consisted of sigma and pi bond. A triple bond would be 1 sigma and 2 pi bond. And around each carbon, you have 3 sigma and 1 pi. Okay, so keep that in mind. So I'm going to write that down actually. This is my bond analysis step. So around each carbon, we need to make 3 sigma and 1 pi bond. Okay, so now the next step we're going to do is to draw out the carbon orbital diagram. Because these two carbons are identical, so I'm just going to go and show you one. Okay, remember that. Okay, so the next step is, what do? Do you remember? Is to promote, right? And then step number 4, you end up with something like this. And then step number 5, you hybridize. Wait a moment. Do I hybridize them all just like before? No, I don't. Because I need to preserve one p orbital in order to form the pi bond overlap. So I'm just going to hybridize these one. So I'm going to make a note and say hybridize these, right? And leave this one for pi bond overlap. In other words, please do not all hybridize this one, the p orbital, okay? All right, so now what would it look like next, okay? So the result of this we're going to see is we're going to form 1, 2, 3. So we're going to have 3 sp2 hybrid that are identical, right? Remember, I use 1s and 2p orbitals, so 1, 2, 3, they look identical this way. And a 2p orbital that hasn't been hybridized at all, okay? So sitting there waiting to overlap with another carbon p orbital. So I'm just gonna split this page up and go up here, all right? So what is the next step? Well, the next step is about drawing, right? So we are going to put the carbon on both sides, and we now know that, okay, I am going to show my sp2 because there's 3 of them. So they're going to situate themselves in a way that minimize repulsion. So 1, 2, 3. These 3 are hybrid. I'm going to shade them just so you see. This balloon here, it belongs to the other carbon, right? So can you guess what the angle is here between the 2 hybrid? Because there's only 3 lobes and the total angle is 360. So this angle here should be about 120 to minimize the repulsion, right? Now, I also know that the other carbon is going to look the same. So I am going to draw something similar as well. So these are the lobes that I'm going to use, right, to make my sigma bond, okay? And I'm just going to shade for the other carbon as well. So now I can bring in my hydrogen that you see in my Lewis structure. So that my hydrogen, that's my hydrogen there. So that's my sigma bond, right? And same thing with the other carbon. Now, where is my last sigma bond? Well, you see here, the 2 overlapping horizontally like that. That is a sigma bond between the 2 carbon. Where's my pi bond, right? So imagine if I have an axis that go through this page, right? That is going to be my z-axis, and the 2 pi bond is going to overlap. Of course, I cannot draw it directly up like that, so I'm going to rely on the paper and just draw 2 axes, right? But on that axis, I'm going to draw my figure 8 p orbital. Now, remember, I have not used this in hybridization. So it's still there at a 90-degree angle to the rest of my hybrids. So now they're going to overlap sideways like that, okay? And I tend to do a little bit of, motion there just to show the overlap. And that is your pi bond right there, okay? So I hope that you see that. And the P lobes extended on top and at the bottom of what seemed to be the plane set out by the three hybrids. And this is what it look like, okay? And if you are going to draw this as perspective drawing, you're going to draw the hydrogen here for me. Sorry, I don't know why I make that line there. Okay, and then if you want, you could do, the dash here, my bad, and this become your wedge. This is your dash, and that is your wedge, just to show this perspective, right? These two hydrogen coming at you, and the other two hydrogen coming away from you. And what's the bond angle here, guys? 120. This, 120, 120 all around, basically, okay? So have a look again at this picture, and I hope that you can bring this to apply to the next one, which is, let me show you, triple bond, right? So it's not very, very different from what we just did. Although I would like to show you a finished product just so that you see. This is what triple bond hybridization overlapping orbital would look like at the end. And one more example that I'm going to ask you to do for me is, could you extend that to atom that would require an octet expansion like phosphorus, right? What would it look like for you? So just to show you the end result, and I hope that you will try these out yourself, is the example of PF5. And by the way, I will be posting this on Google Classroom, just so you can see at the end. Remember that I'm no longer having hydrogen, right? I am bonding the phosphorus with the fluorine atom, and fluorine valence electron is the p orbital. So the p electron would be a dumbbell shape themselves and not just a sphere, right? So that's the difference. And one more time, I think it's so important that you utilize color just to help you differentiate between the plane of different things. So I used a different set of color for the p orbitals. This is the case of C2H2 triple bond hybridization. And you can also see that there's another plane going into the paper, which are color yellow here. So those are the two orbitals that are 90 degree on top of each other. Okay. All right. That's it, everyone.